So I want to talk about something I call cubical type theory. And this is still something in progress, which we are designing in the moment. And it's a joint work with Ambrus Kaposi, who sits there. He's a PhD student in Nottingham. So it's not done, but I think it's a good maybe opportunity to present some ideas and hopefully get some feedback. So the basic idea is that cubical type theory is supposed to be an implementation of what's now called homotopy type theory. And it is based on some work from Chalmers University in Göteborg. So there is this work by Bernardy and Moulin about internal parametricity. Which is very recent. I think it's 2012. And by Bezem, Coquand, and Huber about what's this? A model of type theory in cubical sets. Okay, so that's where the name cubical comes from. So I wanted to present this in some detail, but before I do this, I would like to say some general word why I think this is quite important and why I think homotopy type theory is sort of the type theory of the future. Why I think it's very important. And this is based on a very simple principle, namely replaceable objects should be equal. And this can be also abbreviated with the word extensionality. So, I mean, I think this becomes more important when we do computer formalized mathematics, because so far we can always trust that people will understand if we say, okay, this is a similar proof, you just have to do things a little bit different. But computers are not very good with this. So if we want to be able to replace components, if we want to be able to do abstract mathematics in a way that we can reuse one development somewhere else, and this is the only way to have an effective implementation, we have to be able to replace objects which behave the same, where we can replace unary natural numbers by binary natural numbers, and so on. And for this, it's absolutely essential that we do not can look into a component, that we can talk about intensional properties of our mathematical objects. So in set theory, we can ask the question, is the empty set an element of the natural numbers? And this is really a bad question, right? Because it's a question about the representation, and we shouldn't be allowed to ask this question. This reminds me on when I did programming, and I found out that one program wouldn't run if it starts on an odd address. It would only run from even addresses, and that's something which shouldn't really matter. It's an implementation detail. So we should not be able to talk about implementation details like this. And indeed, type theory doesn't stops us from asking this sort of question. We cannot formulate this in type theory, because in type theory, we have this idea that we first introduce a type and then the elements. And this is quite important for this sort of abstract view. Whereas in set theory, it's first of the sets are there already, and then we start to sort them. So it's quite, in a way, quite surprising that indeed what's called intentional type theory is ideally suited to satisfy this idea, because it does not allow these sort of intentional observations. There's also something which is sometimes known as, or what is known as extensional type theory. And it's quite ironical that extensional type theory is actually, in a sense, anti-extensional. Because in extensional type theory, we cannot define an extensional equality of types or structures, because we are forced to be proof irrelevant. So it is intentional type theory which then gets extended to homotopy type theory, which I think is an ideal candidate for a type theory for a system which satisfies the slogan. However, in the moment, there is a problem with homotopy type theory, namely that the presentation, like the presentation which is also used in the book on homotopy type theory, introduces some axiom, some postulates. And these postulates destroy the computational nature of type theory. So it's like when I talk to computer scientists, I have to tell them that homotopy type theory is a programming language for which we don't yet know how to run the programs. And it's quite fascinating that most of the mathematicians are quite blasé about this, but the computer scientists feel somehow irritated about this fact. So that's something I would like to fix. And it's very clear that this recent work by Thierry Coquand and Marc and Simon give some part of the answer by giving an effective model construction, which sort of shows us that in principle we can run these programs, or we can run programs in homotopy type theory. What I would like to do is start to develop a type theory, a calculus, a system of rules which does this. Yeah? Okay, so let us do this. So first, some general remarks. So I'm going to introduce some judgments. So first of all, I'm going to talk about context, which are sequences of assumptions. Then the judgment that the term A has type big A. I'm not introducing a type judgment, but instead I say A has type U to say A is a type. So U is a universe. And then I can also say that two terms are equal if they have the same type. So this means judgmentally equal, or we also call it definitionally equal. And we also introduced substitutions. So, okay, hang on. Write this. Delta is a substitution from gamma to delta. And that's used like this. If I have a term in A and I have a substitution, then I can, that's called delta, okay. Then I can apply the substitution this way. And note that U delta is U. So this gives us also a rule how we can substitute in types. Okay. Oh yes, I also have equality of substitutions. Maybe worthwhile to say that I have an empty context, and if I have a context, and in this context I have a type, then I can extend this context by assumption. So the contexts are defined like this. And the substitution, there's an empty substitution from gamma to the empty context. And if I have a substitution delta, oh, hang on, I changed the syntax. And in gamma, I have an A, which is an A delta. Then gamma x is assigned to A. Delta x is assigned to A is a substitution from gamma to delta x becomes A. Okay, I don't want to give all the rules, but at least the basic ones. So this is a substitution, it's a calculus with explicit substitutions. And I think there are a number of presentations of this already. Delta, comma, x?
On the right. On the right. You should not have a little a on the right.
Oh, yeah.
X colon.
Yeah, thank you. Yes, please correct me if I say something wrong, obviously. Okay, so the basic starting point is to have a different way we introduce equality. In Martin-Lev type theory, equality is introduced by introduction and symmetric elimination rule. And as a consequence of this, the way equality is defined, we have a principle which is called equality reflection, that in the empty context, if we have no assumption, the propositional equality and judgmental equality agree. But this means we have no possibility. I mean, basically, propositional equality is reflected judgmental equality. It's really given by the judgmental equality if you have no assumption. But the judgmental equality is necessarily not extensional. It's a very, very simple equality. And hence, it cannot satisfy this principle. So if we want to fix this problem, we have to have another approach to equality. And the idea is that instead, we define equality for every type. And we introduce some constants, and then recover, actually, the rules which are given in intensional type theory, the introduction rule, reflexivity, and the elimination rule, which is known as J, as derived constants. Yeah. So the goal is to have a theory which is actually an extension of intensional type theory. So everything which we could do in intensional type theory we can still do, but we have more freedom in choosing the equality, and we are able to choose an extensional equality. And in particular, we fix what I would call an issue in intensional type theory, that we cannot define equality for pi types or for universes internally, while for other finitary objects, we can give an explicit definition of the equality. And the issue here is that the equality we want to define is an extensional equality, which is not, which cannot be the reflection of judgmental equality. So the rule for equality, if you have a type A, then we have a relation in a different context. And it's a heterogeneous relation. So that's an observation we made earlier, that if you want to define an equality in a dependently type language, then it's natural to have a heterogeneous equality, because once you start to talk about pi types, you find it doesn't fit into this narrow framework of having just a fixed equality between the same type. So here, equality, first of all, lives in a different context. So I'm going to give a definition. If gamma is a context, then gamma equal is a context. And it's between two different types. Namely, I have two substitutions, 0 and 1, from gamma equal to gamma. Okay? So it's a heterogeneous equality which lives in a different context. So let us define this context. So for the empty context, it's just the empty context. But for the context extended by assumption, this translation translates gamma, and then we introduce a variable in A0. So using already this substitution here, we know A is a type in U, and given the rule I write on here, A0 is a type in gamma equals, right? X1 is in A1, and X bar is a proof that X0 is equal to X1 in A. So here we introduce a heterogeneous equality based on assumption in the context that all these elements in the context get duplicated and each of them are equal. Okay, what have I not done? Or maybe I should have written 0 gamma, 1 gamma, because I'm going to define these constants also by recursion over gamma. So, and let me write B for 0 or 1, not to have to write the same thing twice. Then B for the empty context is just the empty substitution up there. And B, is this too low? Can I write here? Yeah. It'd be good if B gamma x colon A is given by B gamma, and now I have to assign x to something in the context gamma equals, and it just shows xb. So what 0 and 1 are doing is projecting out these appropriate components. Okay. So now the idea is that this equality I'm going to define for every A. So it's going to be defined by recursion over A or induction over A. Now, for the base type, like studying natural numbers, we know how to specify equality, right? Equality for natural numbers. If it's two zeros, we say yes. If it's successor on 0, we say no. And if they're successors, then we recur. Okay, so that's a good definition of equality. But what about pi types or sigma types? So when is if you have a type A and under XA, no, and we have a B. No, how do I do this? No, sorry. Under X colon A, we have a B in U. then we know that pi x a b is in U. This is a formation rule for pi types. So now, what is pi x a b from f? Let's write them, call them f0 and f1. So f0 is in pi x a b 0, which is the same as pi x a 0, and here b 0, but we have another variable x, which is assigned to itself. So it's not, I don't want to write b0, because this is b0 in the context gamma, and b lives in the context gamma x. So to make it clear that there is an extra x, I write it down there. Okay, so, and the same just with 0 replaced by 1 for f1. Now I have to give a definition for what? For this. And it's not very surprising. I say let x0 be an a0, let x1 be an a1, let x bar be a proof that x0 is equal to x1, and then I want that f0 applied to x0 is the same in B to the end of the blackboard. F1, x1 just fits. And we can check that this relation here has to live in gamma equal, so this one has to live in gamma x colon a equal. And if you look what this means, we just need these three types, which I have just introduced here. Yeah? So the point here is that by using a heterogeneous equality, the rule for the pi type is very simple. And we don't need any transports or any stuff like this. So I guess I'll leave it as an exercise to write down the rule for sigma, right? It's not.
Is it enough to write as little as capital B?
Yes. Because capital B here lives in gamma x colon a.
Oh, so
Yeah.
depends on the three variables.
Yes, it exactly depends on the three variables. Yeah.
Separate this indexing.
Yes. What do you mean? Yeah. 0, 0. Yeah. That will play a role in a minute. Exactly. I can iterate this. Okay. Maybe it's interesting to give the rule for a type. Yeah. Do I want to do this? Oh, yes. No, I want to give the rule for U. Okay, so as before, I'm here for reason for simplicity. I just write U in U. Obviously, that should be fixed, and you should think of UI as in UI plus 1. But I'm not going into this. So then we need a relation tilde U. So when is A related to B? So when are two types equal in the universe? So now I'm going to separate this talk in two phases. In the first phase, I'm only introducing the equality relation and some other constants which allow us to derive reflexivity, but not the eliminator. and then I'm coming to the eliminator later. And depending on this choice, you get a different definition of the universe. So the first definition of the universe is an incorrect approximation, which I'm going to replace later. So the first approximation is A arrow B arrow U, and that's this inspired by this internal parametricity, or corresponds to the idea of internal parametricity. And that's obviously not right. Why is it not right? Because it's not an equivalence relation, right? It says the relation on the universe is given by any relation. And that's it's not an equivalence. So we're going to refine this later by adding more components here. This is the first component of a sigma type. I'm going to add more components. And these components then correspond to also having more constants. And these constants are the Kahn filling operations. So I'm presenting this in two steps. I first present it without Kahn, and then I put these Kahn fillers in. And putting the Kahn fillers in changes the definition of the universe. Namely, it changes the definition of the universe in such a way that this equivalence here, the equivalence of types, is equivalent to the equivalence. To equivalence in homotopy type theory, yeah? With much equivalence. So this is only a first approximation. Okay. So we have defined the types. The other main ingredient is that every term we can define, so it's important, the key property of equality is that every term we can define respects equality. So I'm writing this down. If I have A in A, then in the context gamma equal, I have an A tilde, which is the proof that A respects equality, which proves that A0 is related in A to A1. And how do I define this? Now let's first of all give some trivial cases. For example, what's X tilde? If A is a variable, and then we live in gamma equal, then obviously we refer to the assumption X bar, which we have introduced here, right? Now, what is lambda X A B tilde? Now this is going to be a pi type. A is here going to be a pi type. So we certainly have to have something like lambda x0 in A0, x1 in A1, and x bar that x0 is equal to x1. And I continue on the next line, and then we do B tilde. It would be nice if B tilde would have fit into this corner, right? I expected I write more, but B tilde lives in gamma equal, which just exactly needs these three assumptions, yeah? So there's nothing happening, I'm sorry, yeah? It's just, it works by itself, yeah? But I think that's a good feature, to be honest, yeah? So, and if I have a function applied to an argument, and I want to do the tilde, what is this? So now, not surprisingly, I do f tilde, but f tilde is now a proof of an inequality of a pi type, so it needs three arguments, and these are A0, A1, and A tilde. Okay. So what is if we have tilde for a type? Yeah, I mean if little a is the big A, so let's write A tilde. So if you have here A colon U, then A tilde is U0 related in, no, it's A0, sorry, related in U to A1. Yeah, it's a proof that A0 is equivalent to A1, but these equivalence proofs are a bit boring, these ones. So this thing here just becomes A0, A1, LU, right? And then maybe it's not surprising, what is the definition of A tilde is tilde A, right? So here we close the loop. Okay. So let me tell you a bit more about this equality before I. So what I have done so far, I have defined a equality relation by recursion over the types, and I have shown, or I have derived, I have a constant which I can reduce, which proves that every term respects equality. Now what I want to do next is, I want to introduce reflexivity, because this we haven't done, but I think maybe I want to introduce, at least as a preliminary, the following construction. If I have a substitution, let's call it delta, gamma to delta, I can actually lift it to a substitution of from gamma equal to delta equal. And how do I do this? If I have delta, x becomes A equal. Okay, so I don't write the empty case, because in the empty case it's obviously empty case. Okay, I mean this is a map. So you have to write down a line for the empty substitution. So it's gamma equal, and now we have x0 something, x1 becomes something, and x bar becomes something. And it's not very surprising what it is. It's A0, A1, and A tilde. Okay. So this way we can lift every substitution to a substitution on equal. And maybe now it's a good question to wonder what laws should hold for this. And I guess there's no surprises here, namely that the identity substitution lifted is definitionally equal to the identity substitution on gamma equal, and the composition of substitution equal. So equal is a functor, intentional functor in the theory, and I think this is important. In my view, it's an important difference between this sort of cubical approach, where we can lift, we can go one dimension higher and iterate this process in a uniform way, in a functorial way. And I don't see how to do this in the simplicial setting. So in my view, this is one of the advantages of going cubical. Okay, another remark is, you may wonder something like this. If we have a substitution between gamma, I mean we lift a substitution delta to gamma and delta, but then now we can go project out the components. I mean you can sort of see this, right? That the components are exactly commute with the projection. So it should be, if if you just look at this, should be no surprise that this naturality square also holds definitionally. A little b is 0 or 1. Okay, these. Oh, here. These are the b's, okay. Yeah?
I don't know if you already somehow explained it, or probably not. What do you do if A in there is a variable of type U?
Yes. Let me think. If it's a variable, the rule for...
If gamma itself is just either A in U, and then A is a variable.
Okay. So you have assumption x colon U.
Yes. And A is there.
Yes, but then this comes together with proofs that x bar, x0 is in U related to x1 in the context, right? And that's my relation.
In the equality context.
Yeah, so that's just my relation, right? I have assumed that the two are related.
No,
I mean, if I have this assumption x colon U, then what is x colon U equal is x0 in U, x1 in U, and x bar, which says that x0 is related to x1 in U, and this is just a relation, which is the relation which I'm using to evaluate this.
Okay.
Yeah? You're just stretching yourself, yeah? Okay. Yeah, das ist... Okay. Yeah?
Looking at that form, did you explain what the beta rule is, right?
I didn't. No? So the beta rule is justified, right? I mean...
What is the equality that you're using?
Sorry, so the usual beta rule, yeah?
Is it judgmental equality?
Yes, sure, yeah, sorry. Yeah, beta is, I didn't write, it's the usual judgmental equalities, yeah, I didn't write down the rule for beta, also under lambda, psi rule, yeah. Okay.
What do the calling equals then?
Sorry?
What do the calling equals places?
Colon equal, oh, defined.
Defined.
This is a,
Yeah.
I'm introducing a definitional inequality here, yeah.
And is that also on the left, or you introduce it on the right?
Yes, okay. I'm in my substitutions. I view the substitutions as of definitional definitions. No, as definitions, yeah, of variables. Yeah. Okay, good question. Yeah. And I have to be a bit careful because I'm sometimes introducing definitional inequalities which you cannot just execute by replacing left from right. So maybe I shouldn't really use the symbol, but I'm saying here basically I'm introducing a definitional inequality, or I'm stating a definitional inequality, which is a rule in my system. Yeah. Or sometimes they are derivable, so I don't make this very clear. So down there, it's a derivable, one admissible definitional inequality. Yeah.
So why can't you use this to define your relation for an arbitrary A through substitution?
Yes.
No.
Pardon? No, maybe I misunderstood you.
It's kind of a provocative. It's a question which is supposed to somehow give an answer or no.
Oh,
So,
sorry. I gave the wrong answer. Failed. I try again, yeah.
So you have some rules for what to do with the variable. So with the type which is a variable.
Yeah.
Now, why can't I do? Why can't I define the equality relation on a concrete type by simply substituting this complete type into this general formula.
So in the moment you can do this, because I haven't given the final definition of what equality between types is. Once I give this, the only relations you're allowed to plug in are the ones which are one-to-one. Okay? In the moment, I allow any relation, and you're right, so I can just substitute with any relation, which is maybe not an equivalence. But once I introduce the Kahn conditions here, the only relation you can plug in is the one which is one-to-one. Okay? That's a bug in the moment. Yeah.
I have a question. So your bracket 0 and 1 only apply to types?
No. To everything. I have used them only in types so far, right?
Not on universe.
On universes, I mean, yeah, I mean the universe is a constant, so if you apply substitution, it just disappears, right?
Yes, but even if you have a hierarchy of universe, you would keep this principle.
I think so, yeah, they're just constants. Yeah.
So there is not U of bracket 0, so they're stable when you don't.
Yeah. Yeah, they're just constants. Yeah. Okay. Okay, so reflexivity. Maybe I need a bit more space. It's okay here. Okay, what I'm going to introduce is okay. We have if you look at gamma and gamma equal, we have these two maps, which some people may call phase maps, right? And we also want to have a map in the other direction, which is usually called degeneracy R gamma, right? And at the same time, if I have an element A in A, then I also want that A is related to A substituted R with A. And actually, this doesn't type check because this is in A. So this one is in A0R. And this one is in A1R, right?
What is R then?
Oh, this one here. R is my degeneracy. So obviously, what I want is that this pass here, so 0 after R gamma, and 1 after, this is an R gamma, is just the identity, definitionally. Okay, so that means that this is A and this is A, and hence it's fine.
I'm confused about the unlabeled gamma above. I would have expected that 0 goes from gamma equals to gamma of 0 and correspondingly for 1.
No. The substitution it goes from gamma equal to gamma. I showed this. Right? It projects out.
There is no such thing as gamma 0.
The type is decoded as two types together with a relation between them. Then when I project.
So gamma 0 doesn't exist. So 0. So gamma equals doubles gamma and introduces obvious equalities in between, right? So gamma, the 0, the substitution 0, just pulls out all the 0 components.
Yeah, but it's a different targets, because, you say...
I've written down here. No, here, look. So where is it? 0 goes from gamma equal to gamma, yeah? So I have to say what it is for the empty context. This is the empty substitution, and for an extension, I refer to B gamma, and now I have to say what X is, and it's XB. You're confused, Thomas. I managed to confuse you. Okay? Yeah. So it should type check, at least. Okay, so how do we define? We can define, so here I should be careful not to write the colon equals, but let's just give some equations which should hold. So Raffel gamma of A, if I have a term A, how can I construct its reflexivity? Now I'm going to use the fact that I have a congruence corresponding to A, right? So this actually equal to A tilde substituted R. Yeah? So I'm using, so reflexivity commutes with congruence. That shouldn't be a surprise. Yeah? So how I define R, so I leave out for the empty, but R gamma x colon A is a substitution from gamma to gamma equals. So, okay, we obviously do R gamma, and now we have to put something in for x0, for x1, right, and for x bar. Now x0 is going to be x, because we knew x in gamma, right? We have gamma x colon A, so it's just x. This is also x, and here we have to use this fact, and this is Raffel of x. Yeah. So now I have done. If you use this these definitions, I have cycled, right? Because why? If you start with Raffel x, okay, this is the same as x bar R. So x, but x tilde is just x bar, and x bar in R is just Raffel of x, okay? So these definitional inequalities cannot always be interpreted as rewrite from left to right, okay? We have some normal form, and Raffel x is basically a normal form, which we cannot reduce further, okay?
Is this connected with the U colon U?
No. No, it's independent, yeah. So it's still, so we have to, we state here some definitional inequalities, but the reasoning why this is actually a decidable relation is not as trivial as in intentional type theory.
Sorry, I don't understand what the Raffel is. Why did you introduce it?
Why do I introduce Raffel? Because so I want to model the term in ordinary type theory. So I have now, with this relation here, I have a homogeneous equality, which is the equality type, which replaces the equality type, or is the substitute, the definition of the conventional equality type. And Raffel here is the definition of reflexivity. Right? So that's my program is to give explanation of the usual equality constants in type theory in terms of these. Okay.
Although this looks circular, it is not bad.
Yeah, it's not bad because the point is if you have a term of the form Raffel of x, it's stuck. Yeah? You should not. This is a normal form. You shouldn't reduce this any further. If it's Raffel of something else, then it's useful to move it out.
Can you explain why is ref x occurring twice on the bottom line?
Sorry?
Raffel x is occurring twice on the bottom.
Yes. So sorry, I tried to give a reduction. If a Raffel x is defined here as this, so it's x bar R, but x tilde R, so I did a little derivation, but x tilde I have at some point, hopefully, maybe I haven't, have I not? Okay. Yeah. Oh yeah, x tilde is x bar. So we have a x bar of R, but x bar is substituted as Raffel x. If I carry out the substitution, I'm back at Raffel x. So I'm just, this is just a loop if you just replace from left to right. Yeah. So it should not be read as always replace. This should be read as only replace if A is not a variable. Yeah? Okay. Okay, 8 minutes. What do I want to say here? Okay, let me do I need?
Just ask, is it possible to iterate the equality
Yeah.
sign to get gamma equals?
Exactly, that's what I just wanted to do. No, it's very good. I mean, so I wanted to have a look at gamma equals. And so let's just look at one type, x colon A. So what's the x comma A equal? So first of all, we had x colon A, sorry. So that's just a point, right? And now x colon A equal is x0 in A0, x1 in A1, and x bar in x0 equivalent to x1. And we can draw this like this. This is x0, this is x bar, and this is x1, right? So what happens now if I do x colon A equal? So okay, let me draw this. So I have x00 and x01, which I'm too lazy to write down the context. Should I write down the context? Okay, let's write it down. So here we have this first one, which gets tripled in x00, A00, x01 in A01, and x0 bar, which is x00, is related in A0 to x01, right? And then the same for x1. So I have x10 in A10, x11 in A11, and x1 bar in x10 related in A1 to x11, but I'm not done, because now I have x bar. So I have x bar 0, which relates x00 in A0 and x10, and I have x bar 1, which relates x01 and x11 in a substituted 1. So please, here the substitution is there, and here it's down there, okay? And now I have x bar bar, which relates x0 bar and x bar x0, x bar 1 in x0 is equal to x1 in A. I hope I got this right. Where? Oh, this one. Oh yeah. Okay. Okay, and let's draw this. Here we have x00. Here we have x01, and here we have x0 bar. Here we have x10. Here we have x11, and we have x1 bar. And here we have x bar 0. Here we have x bar 1, and here we have x bar bar. All right.
What are the parameters?
I mean, there's a difference whether you do first tilde and then 0, or first zero and then tilde, and then bar. Yeah, they don't commute. So now exercise till next lecture, do this for 3, right? Okay. So that's where the cubes, the cubical nature of the theory comes from. And as I say, it's very uniform. I mean, we can get all the higher cubes by just iterating this process. And I don't see how to do this for simplices. Or, I'm sure there may be a way, but it seems to be more difficult. So let me...
May I say a few more words about this picture? About this? So this x bar is going from...
It says that these two things are equal up to this equality. This it's just because you have this heterogeneous equality, you can give a type for the filler of the square and the cube and so on. You just iterate this process.
How do you say that sort of that the boundary of x bar is indeed x0 bar and x1 bar?
I mean, I think that follows just from the rules I've given. Well, you can go. we can go through it, but not now. Okay, just I think I'm short of time. I wanted to make one more remark, because in the moment I don't have all the morphisms. I don't have syntactic counterparts for all the morphisms in the cubical model, but actually I need them. And so there's this process. So if you have, there's 2 ways to get reflexivity 1 dimension up. And this is, if you start with gamma equal, right? Then we can go via R gamma equal to gamma equal. And that means the following. If I have a line here, like this one, x0, x1, x bar, I copy it here on top and put in reflexivity here, right? And what was this? This is then refl of x bar, okay? But I can also do something else. This is what I get here. But I can also go R gamma equal. This also goes to gamma equal. But it does something slightly different. You have a reflexivity here. And you plug in your x bar you started in this direction, and then complete the cube like this. And this is refl x tilde, I think. And you see that these two are rotated. So we also introduce a morphism here, which I call S gamma, which in general takes the square and rotates it. And that's all you need, because then if you think about it, you can commute any 2 dimension. Because if you can commute the next dimension and you can lift it with equal, you have all the morphisms you need. Okay. So I'm stopping here. This is the first step, which is inspired, very close to the work by Bernardy, where we introduce a relation. And how else do you define a relation on types if not using logical relations? So that's all I'm doing here. I'm doing logical relations for dependent types. And that corresponds, and that's an observation, to the construction of cubical sets. So logical relations, iterated logical relations with reflexivity, with the degeneracy, correspond to the cubical model. So there's a confluence there, which I think is very useful. So what we have done so far is we have defined a relation for all types. We have this that respects, that equality respects everything, and that we have reflexivity. But there's obviously some stuff missing. We don't have yet an eliminator. We cannot model the elimination principle for equality. And we have obviously the bad definition of equality for types. Okay, and I'm going to fix this. When is the next? I'm going to give another talk, right? Tomorrow. I'm going to fix this tomorrow. Okay, or I try to. Still have some work to do, huh? Okay. Thank you very much. I saw that.
Questions?
So I think I understand what your intentions are. The relation to the cubical sets models is absolutely obscure to me. So I was asking myself during your talk, what would be a notion of model? But that's maybe a question coming later. But what is sort of a simple model where your syntax can be interpreted? So my first thought was, like people working with logical relations were taking, for example, set and then set to the delta one, so to speak, reflexive graphs.
Yeah.
Now you want to be higher dimensional.
Yeah.
The first guess would be to take something like simplification sets. Well, simplification sets not okay to cubical sets, but it doesn't seem to be that. I'm almost finished. The point is, if you take cubical sets, what you cannot do is taking indexing to an arbitrary extent, yeah? Because there, in the cubical sets, you have a finite set of names, and I mean, you don't have this indexing along arbitrary sequences of zeros and one. So it should be something like a Brezhnev model as a motivational example, but I don't see it.
Okay. So indeed, as you say, this is very closely related to this reflexive graph model, which again is also closely related to what Per was talking last year in the US. So if you do this, I mean, if you do the Prishev category over this diagram, you get something which comes close to this, but you don't get reflexivity. You get the reflexivity as a sort of external construction, but not as an internal one. And if you want to have reflexivity as a term inside this theory, you have to iterate this diagram. So instead of having just two levels, you have infinitely many levels.
So these are they called what some guys in higher dimensional globular sets?
No, it's not globular sets. It's exactly the underlying category of the cubical sets. Cubical sets are a Prishev model, and if you iterate this diagram, I mean you have to iterate these projections, you have to iterate this reflexivity, and then you have these symmetries here. So if you just build the composites of these terms, you get exactly the underlying category of the cubical sets.
That I don't see because I mean you can index. I mean the bracket I arbitrarily often, which you cannot do in case of cubical sets because at each stage it's a finite set. Yeah. And then after finitely many steps, you are finished with projecting.
No, but I mean, the objects are the natural numbers, and they are obtained by the successor operation is the equals.
Yeah, but then it's a different side than the one for cubical sets.
No, it has exactly the cubical equalities.
Cubical and co-cubical sets, something like that?
Maybe it's the only around. Yeah.
I just have a related question to Thomas. So, assume you write down all the syntax, all the rules, make sure all type checking works. So, how do you what property do you want of your theory? I mean, do you claim that it's a constructive theory? In what way is it justified?
Yes, so I think the justification here is the intuitive idea that equality should be defined by recursion over the types. That's the basic idea. I just make this precise using this apparatus where I use a heterogeneous equality relation. And then the next step is to observe that the equality we define is substitutive, which is this term. Now we need to reconstruct the remaining components of the representation of intentional equality and intentional type theory. So here's reflexivity, and I said I postpone the eliminator till tomorrow. So that's the idea. And okay, so what you get out, what you should get out, is a theory which is where the extensionality principles are built in, because they are the definition of the equality. So you've seen the definition of equality for pi types is almost extensionality, but as soon as you have reflexivity, it is actually extensionality. The definition of equality of the universe in the moment is wrong, but once I fix it, it will be equivalent to univalence. So you have a type theory which is computationally well behaved. There's nothing gets stuck, and extensionality principles are just built in.
So you say that it has some kind of canonical form property.
Yeah, I mean, that's still something I need to do, but that's something I hope to be able to achieve this way. Yeah,
yeah, because I mean, this seems to be related to what you mentioned in Bernardy and Moulin work. Yes. And there, they justify their theory by, through confluence, strong normalization, and a reduction to they want to calculus of construction, but they're reduced to the pure calculus of construction. Yeah. So I was wondering whether you expect something like that.
I'm not sure whether this reduction is possible, but I don't think it's very essential, at least in my view. What is important is that there is a good explanation for all these definitions, and that they're then reflected by the appropriate computational properties. So what is not clear in the moment is that this relation I specify is actually decidable, but it has got a good decidable feeling to me, if that helps. Yeah. Thomas?
Coming back to my original question, putting it differently, I can't suppress the impression that what you do is highly co-inductive. I mean, because you start with A, then you get, this is a type, and types are such triplets. Then you take the 0 and the 1 component, this is a triple again, and you can iterate this. So, I mean, maybe you could destroy my doubts when telling me which kind of reflexive graph or slightly more general structure would you use for interpreting a discrete type? Say NUT or say 2?
NUT is
like 2. Which reflexive graph or slightly more glorious structure will interpret your type 2, 1 plus 1?
I can give it, I mean, I have not talked about the syntax. The definition of 1 plus 1 is very simple, right? I mean, it's the usual.
Not in the syntax. I mean, I was asking about how should I think about those things. So I understood your answer. It's essentially, I have to think of a type as a reflexive graph. But then...
I mean, for Boole, the reflexive graph is very simple, right? It's just...
Yeah, but then I must look, okay, I have Boole. Then I guess what you take is 2 with the diagonal on it.
Yes, exactly.
But then what the heck is Boole 0? It must again be such a gadget.
The Boole 0 is Boole.
There is some co-inductive sort of thing in it, because you have defined your types together with constructors. When you've got a type, you get 2 types and the relation between them, and you can apply this ad libitum again to those things.
But when you find a number of types,
arbitrarily many.
Sure.
Yeah, so that's precisely what co-induction is. So do I have to think about those things? Maybe is it implicitly necessary to think about those things in a co-inductive way?
I don't think so. I mean, you're right. I mean, if you construct all the objects, I mean, then you have arbitrary repetition of gamma equals, so you get infinitely many, right?
It's like globular sets, but op. You see, because you must be.
No, it's not globular sets. These are not the globular equalities. These are the cubical equalities.
I think the question is, what is A of 0 in case when, like, A is over gamma?
Yeah.
Then A of 0 is something over gamma equals.
No, the other way around. Sorry. If A is in gamma, then A0 is in gamma equal.
Yeah, that's what I meant.
Yes. So A0.
Gamma, then A0 is something over gamma.
I mean, for example, if you have an assumption, a universe assumption, then A0, A1 may be two different types, which are equivalent, right?
Right, but so if you want to have if you want to have an iteration, I mean, this A of 0 is over a bigger context. So, and it's only different from A of 1 by sort of
Being equivalent.
in which way the variables are numbered, I suppose.
No, A0 and A1 can be different, but they are equal in the universe. So they're different but equal. They are intentionally different, yeah, but they are equivalent in this context under these assumptions.
I can formulate my question. I think about cubical sets as defined in the Bezem and Coquand thing. Yeah. So we know what sites they are using. It's prejiffs.
Yeah.
You take an A, which is a cubical set, a particular prejiff. I would like to know what prejiff then A0 and A1 is.
Okay. I think we have to take this offline.
Okay, good.
And your S terms are just permutations? Are you choosing them as substitution? They're just renaming?
Yeah, so they swap. I mean, they swap. What's this? They rotate this cube right there. Do this. But in the middle, then there is a term which is like reflexivity. I mean, there's a similar game going on, right? There's this in term S, which rotates an equality proof to the rotated equality proof, right? Yeah, you only need this one because, yeah, you can.
Yeah, so my understanding is everything is defined. Everything is just a definition. Something is basically Bezem type theory, up to reflexivity, where you have to define to assume the reflexivity on variables.
That's
right. So this is the one point where you add something to the theory.
Yeah.
And the rotation.
Yeah. You need both, yeah.
The rotation can't be defined. You have to assume it.
Yeah.
Okay. Yeah. Reflexivity and so far these are the only two things.
Yeah.
Okay.
Okay. Any other question?
Have you been led to this by first considering the equality superscript as a star, I mean, as a model, the sign of a model, and then purely formally iterating it? Or have you had a model in mind where this iteration makes sense from the start?
So the history is going back, I mean, to this 99 paper, where I try to define equality by recursion over types. And then we later refined this in 2008. But in these papers, we were concentrating on extensional equality of pi types, but we weren't thinking of equality of types in the universe. So at this time, we assumed proof irrelevance, a very strong version of proof irrelevance, namely a judgmental version of proof irrelevance. But if we want to introduce equality of types, that's no longer possible. So now the problem was how to extend this construction to this setting, to the proof relevant setting. And there, this work by first the work by which I mentioned by Bernardy and Moulin was very helpful because it gives a way to do this. We do things slightly different presentation, but the ideas are there. And then when I was talking to Thierry last year in the Institut, where is it? In Princeton, right? We observed that there is a presheaf, a presheaf construction which explains this internal parametricity model. And this is also the same presheaf which underlines this cubical set model. So it's a synthesis of these ideas so far.
And the formalization. You seem to work more syntactically than...
Yeah. So my goal, I mean, is to have a type theory which is presented syntactically, which has these properties. Yeah.
Okay, so let's thank.